Swayam Prabha. Digital India. Educated India.
Welcome back to the last lecture of this module, Computational Fluid Dynamics. In the last lecture, we ended at a point where we saw the Reynolds shear stress equation. We discussed about the different terms in it. You don't need to worry about the mathematical equation of those terms, but some common terms like Reynolds shear stress, those things are recommended that you remember them, but not the complex terms. So, in proceeding in that direction, we are going to study the closure problem. So, the effect of the Reynolds shear stress rho tau ij, as you can see on the slide now, the effect of rho into tau ij on the mean flow is like that of a stress term. Okay. So, I am going to write here rho tau ij is actually Reynolds shear stress. Okay. So, it's like a shear stress. To obtain ui and pressure, so ui is the average flow velocities and pressure from Rahn's equation, we need to model this shear stress rho tau ij as a function of the average flow. So, if you look at the equations, so I will take you back to this where we have written the Reynolds average. Yes, here you see this particular equation, this is average quantity that we need to find out, this we need to find out. Okay, these are the independent variables. All right, dij we also know because this is the average value and it comprises of only, this is the only term that has fluctuations, and this increases our complexity. So, we need to be able to equate tau ij to something that is known or some unknown which we are actually calculating. So, the best way is to put it in some form of an average value. Okay. And to do that, that particular problem is called a closure problem. So, we will go back. Okay. So, as I said, to obtain ui and pressure from Rahn's equation, we need to model this Reynolds shear stress given by rho into tau ij as a function of average flow. This will remove the fluctuations, and this process is called the closure problem. There are elegant ways. The first of the methods is called the K epsilon model. So, in this technique, the model focuses on the mechanism that affects the turbulent kinetic energy. K stands for kinetic energy. So, the instantaneous kinetic energy K as a function of time, Kt of a turbulent flow is the sum of the mean kinetic energy and the turbulent kinetic energy K. All right. So, K of t can be written as capital K plus small k. All right. So, this is small k, this is small k, and this is small k. Okay. And capital K is written as simply half u square plus v square plus w square. Okay. Actually u bar, v bar and w bar. And small k is written as half of u dash square plus v dash square plus w dash square. All right. The governing equations for this are, one we have continuity equation and the other is, so the way we write is, so d dt of tau ij, that is what we are modeling, is minus 1 by rho del p del xi plus del xj into 2 nu plus nu t into del ij. How these equations have been derived we are not going to discuss, but these are the two equations that we use for momentum. See, it looks like a momentum equation itself. So, modeling of the Reynolds shear stress as the momentum equation. So, if you see there is a term called nu t. So, this nu t is the eddy viscosity. So, this actually is should better be called as turbulent eddy viscosity, okay, nu t. It can be actually dimensionally related to kinetic energy k and kinetic energy dissipation rate epsilon through nu t is written as C mu into k square by epsilon. So, nu t we are also able to find in terms of k and epsilon, and we substitute this into this equation, and C mu is a non-dimensional constant, okay, which values we know from experiments. For uniform and isotropic turbulence, there is no production or diffusion of turbulent kinetic energy. Therefore, del k del t will be equal to minus epsilon E. Okay. The turbulent kinetic energy and the energy dissipation can be determined from the following equation. So, now we said that this is the equation which we are going to use for determining tau ij, and that we can use in our average equation, Reynolds average Navier-Stokes equation. Alright, we saw that there are some terms. One is nu t, that we do not know again, others are again like del p bar, dij bar, those are known means the quantity that are in terms of average quantities. So, nu t is something that we yet do not know, and we write nu t in terms of C mu into k square by epsilon. So, again we have two things to again find out, k and epsilon, still we do not know. So, the next step is finding out this turbulent kinetic energy k and epsilon, that is how this equation gets in the model gets its name. And to be able to do that, we have two another equation, one is in terms of kinetic energy, one is in terms of epsilon. All right. And this is production of turbulent kinetic energy, this term here. So, we use these two equations to solve for k and epsilon, and the values of the constant in above equation are Cu is equal to 0.09, sigma k is equal to 1. If you see, C mu was there first, right, correct, and then there is sigma k here, then there is sigma E here, you know. So, there are some terms, there is sigma, there is C epsilon 1, there is C epsilon 2. So, those things are already known. All right, these are the values that we use. So, what we do is we solve the k and epsilon equations, use those equations to find out the turbulent eddy viscosity nu t, put it into the Reynolds shear stress equation, and use it in the average equation of Reynolds Navier-Stokes equation. So, just writing it down, solve for k and epsilon, then nu t is related to k square by epsilon, right, nu t, put this in Reynolds shear stress equation and use that in Reynolds averaged Navier-Stokes equations. It is quite a complex way, but it gives good results. Most of the turbulence model in the world follow k and epsilon. There is one other turbulence model called k omega. So, k is the same kinetic energy, omega is somehow related to dissipation epsilon, but that is also outside the scope, but it is better to remember the name. So, the other model is k omega model, like k epsilon. These are the two world's most widely used turbulence models. Each of them have their advantages and disadvantages. So, another method apart from Reynolds average Navier-Stokes equation for solving the turbulence, for solving the computational fluid dynamics Navier-Stokes equation is called direct numerical simulation. So, in direct numerical simulation DNS, Navier-Stokes equation are simulated numerically without any turbulence model. So, they solve for the exact solution. When the governing equations of turbulent flows are discretized with sufficient spatial resolution and high order numerical accuracy, it is known as full turbulence simulation, FTS. Alright. So, in this modeling, Reynolds number is expressed as UL by nu, where RE represents the ratio of the inertial forces to viscous forces, or Reynolds number. U is the characteristic velocity, L is the characteristic length, or Reynolds number can also be written as L square by nu divided by L by U. Numerator and denominators both have dimensions of time. Alright. So, this L square by nu is the characteristic time scale for viscous diffusion, whereas L by U is the characteristic time scale for advection. The magnitude of inertial terms are much higher than viscous term in high Reynolds number flows. That is true because it is the ratio of viscous diffusion, because the ratio of the inertial forces to viscous forces, right. So, can we conclude that viscous effects are unimportant in turbulent flows? No, it is very important, because turbulent energy is dissipated in form of heat by viscous effects. Okay. Therefore, the viscous effects are very important in high energy turbulent flows. To sustain the fluctuations, the supply of kinetic energy must be balanced by the dissipation of turbulent energy, right. This is important thing, supply of kinetic energy must be balanced by the dissipation of turbulent energy. Okay. So, from the above consideration, what we get is, or definitely outside the scope, the derivation of this, that L by eta is of the order of Reynolds number to the power 3 by 4. This has been obtained. Okay. And this eta is a Kolmogorov length scale. So, it is the length scale at which the energy is dissipated with viscosity nu. Okay. You should remember the order and everything, but the derivation is not required. Okay. So, what conclusions can be drawn from the above expression? This is important. So, L by eta. So, length of the flow divided by the Kolmogorov length scale at which energy is dissipated is the function of Reynolds number to the power 3 by 4. So, if this is the equation, what are the conclusions from it? This means that the length scale at which the dissipation takes place is much smaller than the characteristic length scale, right. L by eta is proportional to Re to the power. So, in turbulent flow, Reynolds number is very high. So, that means L by eta is very high. This means numerator is much larger than the denominator, thus implying the length scale at which dissipation takes place is much. So, eta is much smaller than the characteristic length scale L. Valid conclusion from the equation, correct. The ratio of these two length scale is proportional to Re to the power 3 by 4, as we have seen in the last slide. Second thing is, the energy is passed from large vortices, that means the flow is of the scale of length L and T, to smaller vertices, that is, so because see the dissipation happens at the Kolmogorov length scale. So, the eddies transfer energy to each other, they keep on losing the energy, and until they come in the range of this Kolmogorov length scale, and at this point this energy is dissipated through the heat. So in order to simulate all these scales in turbulent flow, so now you see we have a length scale from capital L to eta. Eta is Kolmogorov length scale, which is of the order of several order of magnitude less than millimeters. The computational domain must be sufficiently large than the characteristic length scale L, correct? So to see, there will be vortices which will be of the length L as well. Okay, so the computational domain must be sufficiently large than the characteristic length L. But also it is important that the grid size must be smaller than this. It is very small, of the order of 10 to the power minus 5-6 meters, and length scale of the typically of the order of, let's say, 1 or 2 meters, or 10 to the power 1 meter, let's say. Okay, so to be able to model all the type of energy in direct numerical simulation, the two things that are important is that the total domain means the study area should be larger than the length L, which is of the order of meters, several times hundreds of meters. But the grid size must be smaller than this Kolmogorov length scale, which is very small. All right. The implication of this is that for 3-dimensional simulation of turbulent flow, we will require at least L by eta to the power 3. That means Reynolds number to the power 9 by 4 grid points. Let's say RE is not very high Reynolds number. Let's see, Reynolds number is 10 to the power 4. So how many grids is needed? RE, that is 10 to the power 4 raised to the power 9 by 4. So we need 10 to the power 9 grids, almost so much high, more than billions, around billion grids, which currently, looking at the capacity of our computational facilities, it is not possible. So these things like RE to the power 9 by 4, RE to the power 3 by 4, those are the values which you must remember. Therefore, the computational cost of DNS is very high. All right. Another such technique is called large eddy simulation. See, in the DNS, one important thing to note was that we had the best accuracy, but lot of computational time is required. LES is sort of a trade-off between the Reynolds average. In Reynolds average, we do many approximations, so the results are not that accurate compared to DNS. But LES is something which is a trade-off between DNS and Reynolds average Navier-Stokes equation. So there is a big difference in the behaviors of large and small eddies in turbulent flow field. We were talking in DNS about the length scales, right? We said that there will be vortices or eddies that are as big as the length of the flow. There will be eddies at the time of dissipation of heat will be very small, let's say order of 10 to the power minus 5 minus 6, which also means that there is actually big difference in the behavior of these eddies, right? Large eddies will have a different behavior and small eddies will have a different behavior. So what are large eddies? Large eddies are more anisotropic, and their behavior is dictated by the geometry of the problem domain, all right, and the boundary conditions. The larger eddies, they will also depend upon the body forces acting, whereas small eddies, they are nearly isotropic, they are very small, they have generally a universal behavior as demonstrated by Kolmogorov, which we have not read in this course, but just take it for granted that these have a universal behavior. Important thing to remember is that the large eddies extract energy from the mean flow. So larger the eddies, more energy will be there, correct, and they take energy from the mean flow, that the flow, real flow, whereas small eddies take energy from the a little bit larger eddies which take more energy from the larger eddies than them. So energy is in form of a cascade. So this theorem is called Kolmogorov hypothesis. Again I am telling it's outside the scope, but it's better to mention that. This is actually a major hurdle in the path of researchers trying to develop a universal turbulence model. What is a hurdle? The variation of eddies from large scale to small scale, and the fact that the large scale eddies are not universal in nature, only smaller eddies are. A single turbulence model must be able to describe the collective behavior of all the eddies. Correct. However, the dependence of large eddies on various parameters complicates the problem. Small eddies is no problem because it is universal. So in LES, the larger eddies are computed with a time dependent simulation where the influence of the small eddies are incorporated through a turbulence model. So we say in LES, two parts, large eddies and there are small eddies. Okay. So they are solved through time dependent simulation, and we account for everything, for all large eddies. But small eddies are so much, the effects of the small eddies is taken through a turbulence model. All right. So our domain size we don't need to be accounting for the smaller eddies. We make our grid such that it captures the largest of the eddies. So LES uses spatial filtering operation to separate the large and small eddies, as I have told you, and the filtered Navier-Stokes equation are used as the governing equation for large eddy simulation. Okay. Now what would be the filter? Filter means up till what time, what length should we cut it? The filter width is set to be close to the size of the mesh. There are some terms that when we in LES use the size of the mesh. One is the grid scale, GS. The scales that are directly solved for on the grid are called the grid scales. For large eddies, their grid scales are used for the large eddies, and for the smaller one there is subgrid scales. So small scales are not captured by those grid, correct, because they are larger in size. To capture those eddies, the grid should be at least smaller than those. So subgrid scale modeling is used for smaller eddies. Now the filtering operation that we have talked about is defined by a filter function g of x comma x dash comma delta as. It's a very complex, but there is a filtering operation that you must know, that in LES we use a filtering operation, right, to cut off the smaller eddies and solve in reality for the larger eddies, and then approximate the smaller eddies using a turbulent model. So this is a filtered function. Delta is a filtered width which is mostly set to the size of the mesh, and this is the unfiltered function phi x dash t. The over bar in phi bar xt denotes spatial filtering and not time averaging. This is very important. So until now, when there was bar, we used to do average in time, but this one is spatial filtering. So average in space. So examples of filtering functions are, there is a top hat or box filter where gx, you see there is a g here, right. This is a filtering function, and therefore this is a filtered function. So gxx can be given by different box filter. It's a different study in its own. All right, there's a Gaussian filter. So remembering the name of the filter is good enough, you don't need to remember those equations. So for 3D computation, the filter width, this is important. The filter width is given by this, you must remember that delta is given by cube root of under root x, under root x, under root y, under root z, where delta x, delta y, delta z are the length, width and height of the grid cells respectively. So you saw what G is and what delta is. This delta is here. All right. So now coming to the governing equations of LES, the filtered momentum equation using the grid scale variables can be written as, so this is again space averaging. All right. The influence of subgrid scale eddies is introduced through SGS stress, subgrid scale stress, SGS, and that is written as tau ij. You see here is a term tau ij similar to the Navier-Stokes equation, and that is written as I uj ui uj whole bar minus ui bar into uj bar. These are again space averaged in LES. All right. Where tau ij is Lij C plus Cij plus Rij. The Lij is the Leonard term given by this. There is a cross term called Cij. There is SGS Reynolds stress Rij. All right. So this gives you a overall idea the differences between the, see we have covered Reynolds shear stress in a little bit more detail. The DNS, the idea of DNS, why it is computationally so expensive has been introduced. We went through the terms like Re to the power 3 by 4, number of grid points are equal to Re to the power 9 by 4. The basic idea of LES, where we studied that we basically use the filtering function to model the large eddies, whereas subgrid scale modeling is used to model the smaller eddies. So information like this, what are the different terms, Leonard term, cross term, SGS Reynolds stresses and things like that have been covered in the turbulence modeling part. Many complex equations are not supposed to be remembered by you, but an overall idea about those equations are whatever required in this particular module. And this actually concludes our module on computational introduction to computational fluid dynamics. I hope you enjoyed this particular session, this particular module of the course, and as always these are the references of the the reference books that you can actually use. And thank you so much for listening, and I'll see you next week.